ongoing, and it's likely that in the near future some of these values will be upgraded. It's a matter of this chronostratigraphic chart is always open, and as far as this International Commission on Stratigraphy is concerned with, is if there are some new information and data that appears and it's quite, let's say, reliable, then this kind of dates are going to be prone to some kind of revision and some upgrade. So as time progressed, as we can see, as we proceed on, here is one of the 2015 chart. As you can see, there is now a larger amount of keys or the golden spikes that have been placed. As you can see, in most cases, this is something that is called the GSSA, is a golden, let's say, spike, but this time around big geological analysis, and it's only placed for the Precambrian. For the Precambrian, we have GSSA, which stands for Global Standard Stratigraphic Ages, because these are based on only on the absolute geological or isotope analysis, and that is why we call it GSSA. Compared to the Phanerozoic, and starting from the Cambrian time and ending up with present time, we now have GSSP, because the major difference between them is that this is based both on the absolute geological aging and the fossil content. One of the ideas that enable geoscientists to actually separate the Precambrian from the Cambrian or the post-Cambrian time is the appearance of shelled fossils at the start of the Cambrian time here, around 540 million years ago. Currently, it stands at 541 million years ago. From there onwards up to present, we have now fossils that are presented either by a shell or either by a test, as we call it as well. Skeletons, as we are going to continue on with you, will only appear somewhere here at the Ordovician and more likely to be actually at the Devonian times, for the reason that the first skeletonized organisms appeared with the appearance of fish, right? Fishes are the major, let's say, ancestors of all the vertebrates, while the invertebrates, of course, appeared much earlier at around 541 million years ago. Does anyone remember any invertebrate that comes into your mind? Sorry for that. From where our history and description of the Cambrian starts from. Does anyone recall? Any fossil remain that come to your mind that is associated with the Cambrian? Gentlemen? At least raise your hands that I'm not alone. I'm not talking to myself. Okay. So any idea, at least any fossils? As I want you, whether we like it or not, this will be a good time to recall some of the fossil organisms. Yes, I hear some noise. Exactly. So we start with the trilobites. We can also use some sponges, and we can use some so-called organisms that especially are characteristic for the Neoproterozoic or Precambrian time, called the stromatolites, which are actually something that enable us to, let's say, have a true body fossil compared to the trace fossils that is normally characteristic for the Neoproterozoic time. So starting from the Cambrian time and ongoing to the present, let's say to the Paleozoic, to the end of the Paleozoic at the Permian time here, we had the trilobites that were more likely to be more common fossils and the ones that possessed a test that enabled this boundary to be discovered. But as far as we're going to proceed on our interesting discussion today, it's a bit of a mixture of both paleontology, history, geology. We are going to give credit to each of these periods and see what are the specific differences and composition of each of these periods in terms of index fossils. Right, in 2019, as you can see, the amount of golden spikes continued to grow. And this is where now we have a good correlation between the geochronology and biostratigraphy, meaning the succession of one fossil group after another. And they have been precisely determined with the help of isotope analysis. And as you can see, more and more keys start to appear. And the first kind of golden spike key was actually introduced in 2019 for the so-called Ediacarian time. And we are going to actually discuss with you the Ediacarian fauna today and give some other kind of characteristics to this. Why are they very important actually? As you can see, the time of the Neoproterozoic that preceded the Ediacarian fauna was something called the Cryogenian time, which actually is a direct indication that the Earth or the planet actually experienced a very global cold event, and that is why it has been called the Cryogenian time. And finally, here is the latest one in 2023 of last year. As you can see, the amount of golden spikes continues to grow. The Ediacarian is the one that is the only golden spike key that has been provided for the Precambrian time. As you can see, most of the geological periods, including the only ones that are still remaining unclear in terms of the geological GSSP position points, are the Triassic and some portions of the Carboniferous. They still not memorandum of understanding among the geoscientists, but otherwise, especially the Cenozoic is all completely except the Bartonian and Langian stages are still, and probably the upper part of the Pleistocene is left without a spike. The Cretaceous, as we can see here, the Albian, Barremian, and Hauterivian are the ones that have the spike keys. A similar situation is also observed for the Cambrian time. It's only the Fortunian and some of the latest geological stage, let's say, epochs that have now been proposed for now, even the Cambrian time. As you can see from the name, especially the last ones, or the topmost, the latest Cambrian times are actually characterized by some terminology coming from China. And as you can see, we will all face the reality and challenges of pronouncing this kind of series and epochs, but nonetheless, it is something that we should really enjoy. For the reason why I'm saying is because this is a true international chronostratigraphic chart, and as I told you, it is prone to changes, and with time, if there will be better sections discovered, both subsurface and outcrop analysis based on both on biostratigraphic and chemostratigraphic indications, these stages might be revised and some new stages might be offered in case if they provide a much complete stratigraphical record. So nonetheless, as you can see, gentlemen, we have the following kind of geological chronostratigraphic chart. As you can see, most of it is dealing with the Phanerozoic Aeonal team, or the Aeon, starting from the Cambrian and ending up with the Quaternary of today. However, if you pay attention, we are only dealing here with like the latest estimate now has even gone less. As you can see, the absolute age of the golden spike for the Fortunian stage of the Cambrian is now estimated as around 538.8, which is not even 540 million years. So as you can see, from 2004 to last year's estimates, they have even decreased it, and that shows us that more and more information is appearing, and more precise techniques in terms of isotope dating have been provided and included. So most likely that within the next 20 years, this value will once again change and we'll have something more precise. But what I would like to kind of focus your attention to is that you can see that the whole entire chronostratigraphic chart is mostly concerned with the Phanerozoic time. But with the Precambrian time, we'll have a very tiny portion. And here we have something called the Hader, right? The time ranging from the time when our planet was initiated, and currently it stands at around 4.7 billion years, around 4 billion years of the hard time. This is a very nasty time where probably our planet was resembling something of Mars or Jupiter at current, if you compare it with other planets of our solar system. From 4 billion years to around 2.5 billion years, we have the Archean. And from 2.5 to around 538, right, like we now know, we have the Proterozoic, which has been further subdivided into Paleoproterozoic, Mesoproterozoic, and Neoproterozoic. Why I'm kind of focusing your attention to this is that if we had fossil remains, right, within the Precambrian time, this chart will probably be extended with 3 more columns here, because if we are to value from and subtract from 4.5 to around 500 years, we have 4 billion years have been placed only within this small portion of the chart, which is very unfair. We can see that 7/8 part, or let's say 1/8 of part of our geological history is present within the Phanerozoic. It's well established based on the fossil remains. As you can see, fossils play a crucial role in the better understanding of the geological history. While the Precambrian, as we know with you, did not possess a test or a hard shell. For this reason, most of the fossils that are present are only identified, especially within the Mesoproterozoic and Neoproterozoic times. And unfortunately, these are not body fossils, but trace fossils. Fossil remains that indicate the activity of the fossil organisms, like trails, burrowing trails, and etc., or feeding points or habitats. But this body itself was not preserved for the reason that most of the Precambrian fossils were soft tissued, and that is why they did not preserve in terms of fossils to be examined like those fossils starting from the Cambrian times and ending today by the presence of a hard part of the shell. So these limitations are very well seen, and in fact, if we were to extend, we'll have at least additional 3 or even more columns representing the Precambrian time. But as we're going to progress with you today's discussion, you'll see that even for first evidence of life goes back to around 3.4 billion years ago. But as I mentioned to you last time, it is mostly going to be presented by bacterial kind of organisms, which let's say they are going to share more of prokaryotic rather than eukaryotic origin, and for that reason we cannot really even call it an animal yet. But bacteria nonetheless is the first kind of organism that gave life, and based on the further evolution, as we are going to see, photosynthesis played a crucial role. And we are going to observe with you how the concentration of oxygen actually transferred the atmosphere of our planet for a highly reducive environment into an oxygenated environment as the one that we see today. And in fact, if we look at the composition of our atmosphere, it probably seems that the air that we breathe and the atmosphere that we see has approximately 2.2 billion years, for events that I'm going to share a little bit ahead with you. So generally speaking about that we now know the basic difference between relative geological aging and what are the techniques behind it, and absolute geological techniques behind it. It will be very much important to mention the kind of oldest rocks that have been so far dated with based on all these techniques, and where are they located, so that we can give some credit. So as you can see, the oldest known individual minerals that are found within so-called zones, zircons, come from Western Australia, and they have been dated at 4.4 billion years. So in order not to write a whole entire billion years, adopt a new kind of technique. G stands for giga, which actually gives 9 zeros, and R stands for Latin year, annum, so giga annums or GA, 4.4 billion years. If you allow me to go back, I'll see here 4.4 billion years. As you can see, the zircons actually date way going back to the Hadean time, or before the Archean. So have a new kind of habit of introducing yourselves and using the new terms. So Hadean time. The oldest known rocks are actually known from the Acasta gneisses of Canada, and they have been dated as 4 billion years. So as you can see, there is a battle in both northwestern part of Canada and northwestern part of Australia and northern part of Canada, of where exactly the oldest formations are located. But in Canada, we have not just zircons, right? The remains of, let's say, minerals of some degraded, let's say, highly metamorphosed strata. But the oldest known rocks are the so-called gneisses from Canada, called the Acasta gneisses. Similar in almost approximate age comes up from the so-called Napier complex found in Antarctica. And as you can see, apart from Canada, of course, the two oldest rock formations are known from some portions of the Gondwana, where Australia was once part of and Antarctica was once part of. But the oldest cratons so far, as you might remember from your course of tectonics, the cratons or cratons are the most ancient blocks, right? And are presented by metamorphosed rocks of deep dynamic and regional metamorphism, granite gneisses and etc., schists and so on, that are exposed and occupy some portions of our continental crust. And the most ancient ones are actually identified in South Africa and Western Australia. And both have been dated going back to 3.2 billion years. So remember that the oldest individual minerals are zircons from Western Australia, dated 4.4. Oldest rock formation is the Acasta gneisses of Canada at 4. Almost similar of 3.9 is the Napier complex in Antarctica. But the oldest cratons, or the tectonic units, in other words, where Precambrian rocks are exposed, are known from South Africa and Western Australia again. And they are dated as 3.2 billion years. So 3.2 billion years is something, if you allow me to go backwards, is somewhere here between the Paleo-Archean and the Meso-Archean time. These are the most ancient groups of shields so far developed. As far as we are going to also discuss our the territory of Kenya, we are a bit lucky that we have ancient rock formations developed, and they are normally known within the western part of the country. And that is where we have the Neo-Archean, the so-called Nyanzian and Kavirondian systems developed. We'll give some more credit maybe next time when we'll meet and discuss what are the kind of rocks exposed there and what are their ages. Once again, their ages were determined based on the isotope analysis. Now, among the Precambrian, we have to use the following terms, as we have just seen with you. We have the Hadean, ranging from 4.5 to 4 billion years, Archean, ranging from 4 to 2.5 billion years. Then we have Paleo, Meso, and Neoproterozoic, ranging from 2.5 to 543. But as far as today's chart is concerned, this is around 538.8. What about that? 8 million years. Another important terminology that will be very useful for you is that if we are to compare with even the current chronostratigraphic chart, the Neoproterozoic is subdivided into, if you go backwards, into the Tonian, Cryogenian, and Ediacarian. In the older books, if you look around, you'll find that the Neoproterozoic is actually subdivided into two, let's say, systems. And in this case, we'll have the Riphaean, which started from, let's say, 1,000 years ago to 600 million years ago. And the Vendian, which ranged for around, let's say, the difference here will be around 57 million years, from 600 to 543. While the Vendian is currently known as the Ediacarian or Ediacaran, based on the fauna, the so-called Ediacara fauna enabled this subdivision of the Neoproterozoic time. But if you look into the older dictionaries and older charts, you'll find the Ediacaran as Vendian. Right, so that was something just as a quick excursion into the Precambrian, but we also should give some reference to the Phanerozoic itself, for the last 538.8 million years. And as you can see, the reasons why William Smith by 1815 managed to map only the formations he did map was the reason that at that time there was no knowledge about the Ordovician, there was no knowledge about the Permian, and there was no knowledge about the Silurian. And also the Cambrian was not really well known, because as you can see, as we're going to further discuss with you, these systems or periods were actually introduced very much by Murchison, the efforts of Murchison and Sedgwick. The only formations that he was able to map was tertiary, introduced by Arduino from Italy. Jurassic, as we had seen with you, from Switzerland, introduced by von Humboldt. What else do we have here? Well, those were the only four, but let's say Carboniferous or Carbonaceous, like they were called here, they were introduced some 7 years after his map, but nonetheless, he used to call them as coal seams and colored them, as you might remember from his map, with gray colorings. And that is something that eventually entered into the chronostratigraphic chart. If you allow me to go backwards, again, pay attention that each of the period or the system has a specific coloring code. And if you are going to generate your own maps, there is the so-called RGB coloring code and C, Y, and K coloring codes that are provided. If you need, I'll always share it with you. You have a look at that. Each of the period has a specific coloring for the geological period, and that is why we color based on the fossil and also the absolute aging the period with a certain coloring. So if you look at the Carboniferous in all the geological stratigraphic charts and even maps, you'll find it are colored as dark charcoal colored or gray. Currently, they have provided this kind of coloring code for it. The other confusing one at times can be the coloring between the Devonian and the Paleogene, but of course you really need to have the coloring code system of RGB to kind of differentiate and to better understand what you're dealing with. But nonetheless, these are the kind of codes that are used and widely applied, and it's a must for you to follow when you're going to generate your own geological map based on the stratigraphy that you're going to deal with. Right, so going backwards to the Precambrian life, we can see that here is actually the rock formations actually developed in the so-called Dales Gorge of the Karijini National Park in Pilbara, Western Australia, where the most ancient zircons and associated also cyanobacteria were actually found. This is the outcrop where, as you can see, almost horizontally layered rocks. If you were to ask what kind of composition they were, well, there's a mixture, but most likely, as you even can see from the coloring, it actually represents and reminds the Precambrian setting that we see around here in Kenya. But here, as you can see, we have some evidence of banded iron formations being present here, and also some cherts that are actually intercalated within this strata on outcrop in the Dales Gorge in Pilbara. And actually at a certain, once again, not far away from there, this is the first kind of, let's say, the most ancient so far stromatolite being examined. As you can see, this is the kind of layering they normally generate, resembling the crust or the core of a tree trunk. And this is where they grow. And as you can see, we have some chalcedony or silica kind of intercalations between here that actually preserved it as a fossil. So this is an image of stromatolites that has been aged or dated as 3.5 billion years, and it comes out from the Dresser Formation in Western Australia. And as you can see, in terms of fossil preservation, we had some processes that actually induce preservation, and in this case we had pyritization. As you can see here, fool's gold, the iron sulfide pyritization actually enabled the better preservation, or the model of preservation of this fossil remains. If we were to go further on, as you probably heard today, we are going to talk very much about plate tectonics, and the earliest kind of confirmed case of plate tectonics that has been presented by the maps goes back to around 750 million years. And if we are to look at it, it actually fits within the Neoproterozoic time. And as you can see, this was the location of various kind of, let's say, plates, tectonic plates, on how they were located. If you were to ask where Kenya or East Africa is located, it's somewhere here. As you can see, you have Madagascar and India as a separate block. It's somewhere here. And here is where we have the so-called subduction, and the plates. There was a collisional setting, and that led to the formation of belt. This is where we have the Mozambique belt, and this is where we were located. On the other hand, this is how Kalahari was, and this is a separate Congo block. This is just before the amalgamation. This is when we had the so-called Rodinia. This is the first supercontinent that preceded the well-known Gondwana. But before we know the Gondwana and the Pangea existed, we had the Rodinia superterrain. And this is the way the various kind of blocks or terrains were actually located to one another. East Antarctica was located here, almost at the equator. Australia was north of the equator. South China was a separate block. Then here we have Laurentia, which includes both North America and northeast part of Europe. Baltica is the north part of Western Europe and going to Russia as well. North China was around here. Siberia was a separate block here. And Amazon, which currently into the composition of Brazil together with West Africa, will actually generate this kind of arrangement of the terrains. So here you have 750 million years ago, just after the initial break up of Rodinia super terrain, the dark green shading represents the terrains with good paleomagnetic data. That is another kind of technique that is widely used, and we are going to give some credit, additional discussion, completely separate discussion on in terms of on how it was determined, the motion and the rates and the direction of the plate move easily determined based on the paleomagnetic data, because as far as we geoscientists are concerned, any especially igneous rocks, when they kind of solidified after the eruption, and especially if they have in their composition magnetite and gamatite. These gamatite and magnetite crystals are normally going to be aligned to the position of the paleomagnetic pole. And based on this, we can eventually reconstruct and place exactly the location where the rocks were and how and where was the pole, magnetic pole at that time. And this is the kind of reconstruction that is based on that data. Now, in light green, the one that we have here, is still based on paleomagnetic data, but is quite poor, so much lower resolution compared to the dark green one. So as you can see, if we were to look at ourselves, the best mapped areas are, of course, the Congo block, the Australia, Laurentian North America, and Europe, Baltica, India, quite placed based on somewhere here, and it's not even clear where exactly, but looking at the neighborhood, I suggest that we're somewhere far in the northern hemisphere at that time. Red areas normally indicate I expect us to be somewhere here, but though we have been there's some Kalahari here with terrain, and it's like here, so here and here, that is our location. As we proceed on this time, it's during the Ediacar time. And as you can see, Baltica, which is the north part of Europe and some part of Russia, Laurentia here is the location of both North America and some parts of Western Europe. There were but the so-called Iapetus Ocean. Please take a note of this because it's going to be quite important. This is where the first rifting events did start to occur. I didn't heard. Is there a question?
I'm getting you.
Now, the other beauty of this chart is just it shows that most of the so-called BIFs, the banded iron formations with which, in particular here in Kenya, we are very much having some hope with, developed in the western part of the country around Lake Victoria, is that banded iron formations are a direct indication of reducive environment. When we talk about reducive environment, it means that this is when gamatite and magnetite accumulated among chert and other kind of rock formations, mostly of, let's say, there is also some amount of shale composition, which eventually turned into slate. Only in reducive, in low oxygen concentration environments. And then since, let's say, the early Proterozoic times, you can see that the banded iron formation actually ceased in its formation. So if you people are going to do some analysis and some kind of work in terms of iron exploration activities. Remember that the major iron formations are related with the Archean and the early Proterozoic times, for the reason that the concentration of oxygen was low, and that means that the environment was reduced, and that actually impeded the massive development of magnetite and gamatite deposition in a sedimentary environment, again among charts and other slate kind of or shale deposits in the geological past. So as the oxygen continued to increase, as we can see here, we now have the first evidence, especially in the middle Proterozoic, is there we have now the so-called continental red beds and abundant marine evaporites. So immediately, what does this imply in terms of sedimentology is that the concentration of oxygen was very high. And if we have red beds, that means that all the formations, including banded iron formations that were exposed, were very much prone to weathering, both chemical and physical weathering, and that eventually led to the formation of these so-called red crusts. Again, they are quite common in the western part of Africa and some parts of Central Africa, from Chad going onwards to around Liberia. That is where you have all these so-called crusts, very weathered and heavily weathered crusts. On the other hand, with the increase of oxygen in the atmosphere, we also notice that in some cases we can also associate it with some glaciation or glacial or cold winter environments. Like the first evidence, the first ever recorded glaciation event happened in the early Proterozoic time. And as you can see, it further followed without kind of no activity so far. But then again, as you can see here, we had the Cryogenian Proterozoic, the so-called cold environment, especially in the late Proterozoic Cryogenian. And it also happens to have occurred in the interim time where we had the Ediacarian fauna now occurring. And as you can see, for those people that are now very much concerned about global warming and so on, you can see that the concentration of carbon dioxide also tended to reduce and also to increase. So whatever we're observing in terms of climate change today also happened in the geological past. But once again, we do not have much information that can give us or provide us about the rates under which they occur. But nonetheless, as you can see, the concentration of both oxygen and carbon dioxide plays a crucial role in both the global warming and cooling of our planet. So as you can see, the cryogenic, let's say, stage or cryogenian system or period of the late Proterozoic was characterized by massive glacier activity. And what happened here is that scientists believe that it actually was the first glacial event that almost wiped out all the prehistorical groups of organisms. And as you can see here, we have Ediacarian fauna that happened to occur here within the interglacial time, ranging from around 564 to 543 million years ago. With the increase of oxygen, again, another stepwise increase of oxygen, we can see that animals, in particular these prokaryotes and eukaryotes, now tend to diversify. That continues on until, as we have agreed with you, what actually separates the Precambrian from the Phanerozoic is the first appearance of skeletal fossils. I'll not really call it skeletal because what we want to know is not that the skeleton of the one that we understand is typical for, let's say, vertebrate organisms, but invertebrate, I'll call it invertebrate organisms that possess a text or a shell, now appears at around 543, but according to our latest estimation is 538.8. Now, the first plant organisms, as you can see, appear almost 120 or 30 years later at around, if we look at 410 million years, that takes us to the lower Devonian time. Now, the first land vertebrates even appeared later on, And as you can see, the vertebrates, unfortunately, we do not have the estimation here of fish, but if we look at the fish, which were the first marine vertebrates, they did appear within the Silurian or Ordovician Silurian time, going to around 550. The amphibians, they only started colonizing our planet around 250 million years ago, which actually takes it to the Permian time. And then around the diversity of mammals to which we human beings belong to actually started around 50 million years ago, which actually takes us back to around the Paleocene, or to be more precisely, the Eocene times. And as we're going to see with you, whether you believe it or not, but the first mammal to have appeared and lived almost 65 million years ago or even earlier were nothing else but tiny mice. So this is the kind of biological and the geochemical and other kind of evolutionary developments of our planet that has been observed both on the fossil content and also within the rock record, provides us with a perfect understanding of the development of our for the first isotopic indicators, normally going to be presented by biomarkers, are more than 3.7 billion years, and the oldest prokaryotes actually are around 3.4 billion years. But it's still under a dispute, and there's a still further discussion ongoing between the scientists. The phylogenetic relationship among the three major groups of organisms that actually give life to any group of let's say, animals and plants, they can be subdivided into the following groups. We have the eukaryotes, we have the archaea, we have the eukaryotes are the more better organized than the more complex ones, and these archaeobacteria and eubacteria are actually prokaryotes. So eukaryotes are the ones that actually even give life to us, and this is, we as human beings, we fall into this group of animals, and this is the kind of phylogenetic kind of trend of events that of the major difference between eukaryotes and this group of prokaryotes here is that eukaryotes, they are more complex. The cytology or the construction of the cells is more complicated. They have a nucleus, they have some mitochondria, and they have DNAs and genes compared to these prokaryotes, which tend to do not possess either bacterial appearances, right? And as you can see here, if we were to look at the archaeobacteria, which actually almost appeared at the same time with the eukaryotes, they are presented by various kind of groups that are very even difficult to pronounce. But as you can see, the ones that are quite important here will be the so-called green non-sulfur bacteria. We have the cyanobacteria, which will also give some credit a bit ahead. The green sulfur bacteria, among the eukaryotes, plants, like I call them, the red algae belong here. We as animals, the fungi, these are all eukaryotes. So that is the major kind of difference between them. So the shaded clades include phytosynthetic members, those ones that actually develop and grow based on photosynthesis on the major kind of process involved in photosynthesis is the transformation of inorganic matter into organic matter with the production of oxygen as a byproduct. If time will allow us, I'll even provide you with a specific formula that actually indicates this process. So in general, all the kind of life from which everyone actually developed, or both animals and plants and also the bacteria, can be subdivided into these three branches, as we have seen with you. And these are normally called the three branches of life, in which all deep-seated branches are the so-called hyperthermophilic bacteria, as shown in bold. Now, time increases along the branches, but does not necessarily go in a linear fashion or at the same rate in each branch. Longer branches relate to a faster evolution. So everything started up with this so-called thermophiles. What does that stand for? Thermophiles means temperature, and philes, those ones that can accommodate. They are more likely adaptive to those environments. So the first archaea that developed, they were more thermophile, meaning that they could survive under high temperatures. On the other hand, we have a term called halophiles, which stands for the salinity halo, and philes, once again, adaptive environment. So both the archaea were halophiles and thermophiles. This gave rise to the cyanobacteria, or the bacteria themselves, which eventually later on developed into a group of cyanobacteria and heterotrophic bacteria. And then another very important group came out in the eukaryotes, where most animals and plants actually belong to. As you can see, we had various kind of basal protists, we had the flagellates, we had the rhodophytes, alveolates, the chromists, the plants, the animals, and the fungi all belong to this eukaryotic group. So that is something I understand that probably it might be a shock to you, but this is a I call it paleobiology, and it kind of brings living organisms and so on classified both in the fossil and the current group of animals and plants. So here are some of the shots that provide us some photographs of Neoproterozoic eukaryotic fossils and how they, as you can see, these are the first representatives, and these actually are representatives of the so-called Ediacaran fauna and flora. Most of them, as you can see, at least this fellow here, we can see very nicely that it has a nucleus, and probably these are some of the remains of mitochondria, and this eventually classifies it now into an eukaryote. Here we have something that looks like a worm, like a trail, but it's something still, either it's a trace fossil or it's a body fossil that is still a matter for deep global-like kind of structures presented on the top part of this chart. So if we were to take, once again, this is another, it becomes now more easier to make some kind of explanations of what is going on. Here, as you can see, we have Proterozoic rocks in modern continents. And as you can see, the green one are all representing the extent of the Proterozoic rocks. So on a global scale, they are seen actually throughout the world. And here is a group of scientists headed by a world-known paleontologist called Scotese, and here are some of the Scotese maps that actually now show the location of the paleo blocks, how they were located on a more advanced paleomagnetic and also isotope studies. And as you can see, the major organisms at that time were presented by green algae, coelenterats of the cnidaria, that is jellyfishes and the associated groups. Then we had the pteridium, some prior arthropod that were the ancestors of the trilobites. On the other hand, we had also sponges, and finally we had the pre-arthropods, another group of pre-arthropods that were probably gave rise to the trilobites and so on. The other kind of important, probably, let's say, marine environment that you should always bear in mind is that apart from this, let's say this, when all these masses were almost amalgamated, they generated the Pangea. As you can see, this is Pangaea. We have West Africa, Florida, Laurentia here, quite separately, who are quite located in the vicinity. When all these masses were quite amalgamated into one cell, the other part of the globe was actually occupied by the large ocean called the Pantalassic Ocean. In fact, this is the prior or the pre-Pacific Ocean depression that has always been a depression ever since the planet actually developed. In fact, there has been some assumptions that why is it a depression and it has always been a depression is because probably you've heard that there was a likely impact or collision between a moon-like planet with our planet. They kind of collided, and from that piece we have the moon that generated, and on the other hand, the other components of the other planet were completely destroyed and they kind of dispersed in the space. But that collision led to a kind of crashing out of most of the Pantalassic basin of the ocean, and that is something that has been is what the Pantalassic Ocean stands for. If we were just to reconstruct the Precambrian environment, this is exactly what you are likely going to see. As you have seen from the previous chart, the atmospheric composition was mostly of carbon dioxide, and carbon dioxide was largely incorporated into the atmospheric composition through massive volcanic eruptions, as we can see from this cartoon. So the atmosphere was completely reducive, no free oxygen, and the only organisms that could thrive were actually bacteria, and in this case we have the cyanobacteria and also the stromatolites that were both halophile based on the very acidic and even saline environment. And as you can see, the seas at that time were pretty much shallower compared to the present seas that we see, except for the Pantalassic Ocean, which has always been of deep nature. And here, as you can see, there is no free oxygen, so there is no kind of life possible. Only the organisms that could thrive, right? Bigger, Samuel?
Yeah, I'm asking.
Yes.
What could be the estimate of the Pantalassic depression, please?
The estimate?
Yeah.
In terms of age?
How deep?
Depth?
The depth.
The depth. Well, you see, it's a good question that unfortunately I can't give you any answer to, but if we are to compare and to look at it, it seems like it has always been a depression as far as we have seen it in today's Pacific Ocean. As you might know, the Mariana Depression currently in the Pacific Ocean, not far away from southern Japan, estimates around 12 kilometers, right, if you look to the Mariana Depression. So if we were to suggest that the Pacific Ocean of today is an descendant of the Pantalassic Ocean, then it most likely seems that the Pantalassic Ocean has always been deep, or going to a couple of kilometers in depth. And of course, if we follow the theory according to which there was a collision within our planet with another kind of moon-sized planet that led to the crashing out and actually caving out of this depression that is now occupied by the Pantalassic Ocean, we might assume that it might have been a couple of kilometers for sure. But I do not possess any information about that. But if you can always dig. Maybe you'll find somewhere in the internet or in any other book that can give the exact estimates. But so far, as you can see from the reconstructions, it always seems that the Pantalassic Ocean has been the deepest depressional part of our globe since prehistoric times, going back to at least 650 million years going backwards. I hope I managed to answer.
Yeah, so it means that this region, the Parantarasic Ocean, has never been affected by the subsequent, tectonic movements.
No, why not? As we are going to proceed on, as you can see, here we have the Pangea, right? So what has happened is at certain points you have how do actually these plates move relative to one another? You must recall that we have normally at least three plate tectonic boundaries. We have the convergent, which eventually lead to the collision of some continental blocks. We have the divergent, where we have the rifting, and we have the so-called preservational, or the so-called strike-slip movement, and that is where you have just like the San Andreas and other kind of faults that are related or classified into that. All of this globe, like we're seeing it right now, even from this figure, represents the crustal portion of our planet, and it's always under constant movement. These plates are always under constant movement, northwards, southwards, whatever, wherever they normally decide to kind of move, and what are the stress and strain parameters that control them are normally controlled by these fault boundaries. And what we can see here is that at a certain point, some portion of the Pantalassic Ocean had also experienced some subduction, right? There was some subduction boundaries here through which the Pantalassic Ocean eventually observed or experienced a subsidence and was consumed into the interior. So it has never, of course, the major, as you can see, the most part of our world even today, 70% of it is covered by oceanic and marine environment. So that has been something that has been more or less stable for the last couple of billions of years, as we can see from this chart. But of course, we also have the Pan-African orogeny and other inversion processes that have led to the inversion of all these tectonic blocks relative to the sea level and their uplift for a certain reason, once again controlled by plate tectonics and their boundaries. So once again, the extent and the size and probably the depths of our ocean, as you're asking, they might have experienced some probably deepening or might have been experiencing some shallowing. Unfortunately, the data that we so far possess, as you can see, the time scale, if we go further on, as we are going to have the next kind of slide of here, of the late Cambrian. As you can see, the next slide is 514 million years. What happened between 514 and 650 million years? It's 100 million years in between them. We still do not possess enough data to make a more precise understanding. It's on a global scale. You should understand that the amount of information that was used even to generate this map is enormous. It's a global stratigraphic attempt to reconstruct the paleo environment. But based on the data that we have so far, we can only provide some separate slices. I hope I managed to answer your question.
Yeah, thank you very much.
But nonetheless, this process are still ongoing, right? There's somebody else who has raised his hand. Hello?
For me, my question is just with regards to the concept of the uniformitarianism.
Uniformitarianism.
Yeah, where the presence is the key to the past.
Yes.
I'm just trying to relate. If the presence can be the key to the past, it means the presence can also be the key to the future.
Exactly. And that is one of the ideas that we ended up our last time, our discussion, that is something that can be used. The present can be also the key to the future.
Yeah. So I'm just wondering, there's some events that took place in the past, like the one you have just mentioned of our planet colliding with a moon-sized space body.
Yeah.
And I'm just asking myself the chances of such kind events happening in the future. Leave alone, we have heard of meteorites also falling on the Earth's surface, but I'm just wondering of another more severe, like in those past events we have had the moon-sized bodies colliding with the Earth. So, what are the chances of the such events happening in the future, and what might be the impacts if it can cause maybe the depression of such a wide area occupied by the Pacific Ocean?
Yeah.
So, as humans, I'll
We are
say,
doomed. We are doomed. That's what we can say. If something of this kind happens in the future, we are doomed. And but so far as we can see, there's no, at least what NASA, unfortunately, everything is with NASA currently. And there have been some kind of speculative, and there's a movement of these guys that normally the conspiracy theories that are also mentioning that there's something that is about to happen that NASA is hiding, and there's a kind of a nebula, something they're calling it a nebula that has been seen by NASA, and it's approaching our planet, and that in the future it might collide, and it's very near. This event may happen. Of course, we should understand and always expand our understanding of our planet in a, not only on a planetary level, but in a, let's say, in a space level, or even in an interstellar level. You have probably heard about the black spots or the black dots in our universe, area where the density is so high that it actually consumes even some of the galaxies. So once again, you should always think that this all entire processes that we see, even the weather on our planet right now, is very much interrelated between not only the geosphere and the hydrosphere and the atmosphere, but it also includes the positioning in this outer space, because everything is moving. Even the whole entire solar system is moving around the universe, and its position in the Precambrian and its position today is pretty much different. You have probably heard that the whole entire universe is experiencing an expansion event, right? We are expanding, and that is why the universe is kind of eternal, and not really eternal, but it is so broad that we can only, based on our space instruments and shuttles, we can only cover a certain portion of it, because it's expanding on a continuous level. And where will that end? Well, unfortunately or luckily, we might not know, because our lifespan, again, is quite limited. But once again, if you are asking if such kind of events are likely to happen in the future, of course they might happen. We never know, like the potential life of our sun, which is a star of our galaxy, is given like for another couple of billions of years. What will happen at the end of this term? Of course, it will eventually start to expand. And once it will expand, one of the events that lead to the kind of maturation of each or any kind of star is its expansion. And once it's expanding, it will eventually consume Mercury and Venus, right? Those will be the first planets that will eventually be consumed. Our planet Earth is also in a very shaky position, since being the third one after Mercury and Venus. It can also be consumed, or it might, flow somewhere else, and it can be consumed by another star. We never know. The kind of prognosis that the astrophysicists have is actually a time of very doom understanding, and luckily for us, our lifespan is very low and little, and we are not likely to experience something of this kind. But of course, you can always refer to Hollywood, which always comes with this kind of, frightening kind of pictures, and the imagination goes beyond that. It will kind of consume the whole human society. Yeah, you don't need even to go that far. You can have an idiot that can play a nuclear weapon, or press a button and send us all to wherever we go after that. So I don't think that we really should be concerned about it. But apart from just this kind of assumptions. NASA is always warning that unfortunately there might be some kind of asteroid. There's behind Mars we have the asteroid belt, and these asteroids and comets and meteorites, they tend to kind of experience massive movement. And more likely that in the next coming hundreds of years and the next centuries, once again we might experience some sort of bombardment. Whether that will happen, once again, it's a matter of time. And it's an open debate. When will it happen? No one knows. But whether it may happen, of course it may happen. Can it impact the plate tectonics? Sure, it can. It can kind of ignite the plate tectonics, and in fact, it can even induce the movement at a certain rate that can even resemble the Precambrian time, under which these plates moved hundreds and thousand times much faster than we observe them today. So it's once again a tight interplay, and it goes far beyond even our discussion today. But nonetheless, this process do repeat, and it's if this concept of this concept is also known as the concept of actualism, right? You can easily use another kind of term. So the processes that occur today are likely to occur in the future, and they're likely occurred in the past. So these are the concepts that can be widely applied, and luckily or unfortunately for us, our time span is very short, and we cannot focus and give an idea. But the observations made by NASA satellites suggest that we may likely experience something of this kind. On the other hand is the impact of the location of the moon and the sun can also influence, it has also been confirmed, influence and impact the seismological events, and they can even induce large seismicity, large earthquakes on our planet. So as you can see, this process should be observed in a much broader and integrated approach, apart from what we have been so far seeing so far. I hope I managed to answer your question.
Yes.
So as we proceed on, these are some of the pteridiums. These are the first kind of so-called almost leafy kind of, let's say, amoeba, as you can see, floating. These are first group of the so-called the cyanobacteria, actually the ones that actually generate this kind of substratum of the sea, of the Precambrian sea. Some weeds, as you can see around here. So most of the life that existed at that time, first and foremost, what comes out from this cartoon is that there were soft-bodied organisms, and the only traces that we are likely to observe about them is just their traces, and probably some imprints, some who can tell and remind us what are the prints that we normally observe in terms of paleontology. We call them casts and molds. That is what we are likely to observe from this soft-bodied tissue. So as you can see, the marine environment was quite shallow. Once again, other evidence also shows that if we go backwards to this slide, the atmosphere and why there was no life above this water, which actually prevented it, was that the atmosphere was heavily bombarded by the sun rays, which actually induced high radioactivity event. And that actually, it's only by the Silurian and Devonian times when plants now started colonizing the Earth, that is when we had the ozone layer preventing us from the harmful ultraviolet rays. But before that, these ultraviolet rays, if anyone even dared to sneak out and have a look at the sun or take a sunbath, it had a second or two to think backwards and go back to the water. Because if you were found above the water, you just perish immediately and evaporize, if that is the case. So here is actually some of the components of the stromatolites, and actually the stromatolites, there was a large debate whether they are of organic or inorganic origin, and the first kind of conformation came up with the discovery of the so-called gloecapsomorpha cyanobacteria with the help of scanning electron microscopy and other microscopic techniques, and eventually this is how this bacteria, layer by layer, generates such kind of structures. And that is something that is related to gloecapsomorpha cyanobacteria. So finally, we now go into the next already post Precambrian time, and we start with the Cambrian. And as you can see, once again, referring to the Scotese map, this is a map of 514 million years ago. We can see that, of course, the center, the equator, we had the so-called Laurentia, which included the North America. And you can see United States was actually aligned and cut by the equator just by half. So the east and west was actually north and south at that position based on the paleomagnetic data. So as you can see, apart, as we had noticed with you, that around 700 or 500 million, more than 700 million years ago, the rifting between Baltica and Laurentia continued, and that eventually opened as the so-called Iapetus Ocean. So Baltica, just to be more precise where its location, this is where now Norway and Sweden and some Baltic states are located in. Laurentia includes North America and Canada. Siberia is partially here, Kazakhstan is here, South China is here, and Gondwana, as you can see, all of our continents, the ones that we know as South America, Africa, Australia, Antarctica, India, the Seychelles, and India itself, they are all located within this edge of the planet. And that eventually shows us that, as you can see, after the inversion, we had the so-called Pan-African mountains developed, and that is something that eventually led to the uprise of our continents relative to the Iapetus and the Pantalassic Ocean. As you can see, this now gives a reply to Samuel's question whether the Pantalassic Ocean experienced any change. As you can see now, compared to the previous chart, Pantalassic Ocean is now a northern hemisphere ocean. So as you can see, the crust does move and the plate boundaries do change, and eventually they change the position and probably also the depth. But the position, the geographical position of each of these oceans and continents also affects the temperatures and the climate under which this formation occurs. Now, if we were to increase a bit the fossil content of this time, we will notice that here, first and foremost, we have the group of foraminifera does appear in the Cambrian time. We have sponges also, quite not really frequent, but they do appear. Corals appear much later at the end of, let's say, the Cambrian time. We have the bryozoans, we have the brachiopods, they do appear in the Cambrian time. Who else do we have? Gastropods also are present here. Don't seem to see who else. The ammonites, those ones are already of Mesozoic times. So who else is probably the trilobites? Of course, these are the ones that dominated throughout the whole entire Paleozoic until they perished in the end of the Permian time. Here we have the ostracods are also present, and other kind of starfishes and so on. So the major group of organisms that thrived during the Cambrian period were annelid or worms, coelenterata, these are corals, trilobites, these are some of the arthropods, the onychophorus, lanceolate, and the mollusks are the major kind of Cambrian life forms that existed at that time. If we were to look at the geochronological timescale of today, I think the Cambrian existed from 538 to around 485 million years ago. That was the range under which it existed. Now, a very important part of what we need to memorize is the boundary on how the various kind of periods now of the Phanerozoic system are based on or placed on. And in this case, we need to give some reference to the basal part of the Cambrian system is currently placed on the appearance of a trace fossil called Treptichnus pedum, which is around 2.4 meters above the base of the second member at the Chapel Island of Newfoundland of the formation. And Newfoundland, to be more precise, is between, it's actually shared between US and Canada. So it looks like this is in US. The next system, as you might know from the periodic system, is the Ordovician, and it's actually placed on the first occurrence or the appearance of a conodont. That will be another group of organisms that will give brief credit to. In fact, the only remains that are left from them are their teeth, phosphorus teeth, and long there wasn't an idea what exactly these organisms are. The rest, they remind us a snake, right, or a snake or an eel. There were soft body tissues. The only solid parts were the teeth, and that is what they are called, the conodont. And the name of that conodont, be prepared for Latin, Iapetognathus fluctivagus. And that has been placed, once again, not far away from Newfoundland again, the Greenpoint Formation, at Greenpoint in western Newfoundland, in bed number 23 at a level of 101.8 meters. And that is why, of course, I'll advise you to probably dig in the internet and figure out more, if you allow me to go backwards a bit to the chronostratigraphic chart, and we'll see that we have the Fortunian. So as a homework, please deal with the Fortunian stage and see whether the 538.8 million years is actually based on the first occurrence of Treptichnus pedum, the trace fossil. But so far as I remember, it's still under the Terranovian epoch or series of the Cambrian system or period. Figure out whether the Fortunian stage is determined by the first occurrence of Treptichnus pedum. On the other hand, as I've mentioned, the top of the Cambrian is now estimated by the first occurrence of a conodont called Iapetognathus fluctivagus. Be prepared, there's a lot of Latin, and this is a must for you as masters to kind of mind and remember that. And actually, here is actually the trace fossil. Here it is. And this is how Treptichnus pedum is normally analyzed. As you can see from its age, it actually existed from the Cambrian and went up to the Cretaceous times, up to the mid-Cretaceous, up to the Cenomanian stage. That is when it disappeared. Again, as you can see, apart from biostratigraphy, we have now chemostratigraphy. And chemostratigraphy, we come with isotope analysis. And the absolute ages of both the base and the top of the Cambrian system are based on recent uranium, lead, zircon dating of volcanic deposits intercalated with sedimentary succession. Of course, my estimates here are quite outdated. As you have seen from the new chart, it's no longer 542, it's 538.8. And the maximum age of the Cambrian Ordovician boundary has recently been estimated from the latest Cambrian volcanoclastic sandstone beds, located in North Wales, and they have been placed at 489.6 million years. A minimum age of 483 is based on Tremadokian ash based in Nova Scotia. So as you can see, absolute ages are normally obtained based on isotope analysis. And as we have noticed, in this case, zircon, which is zircon silicate, is the one that is extracted from volcanic deposits that are intercalated among sedimentary rock units, and is the one that is tested on both uranium and lead. Absolute age analysis. Right. Samuel, you have a question?
Yes, I'm wondering whether this volcanoclastic is the same as volcaniclastic, because I don't expect at this time to have experienced volcanicity, or is it a different meaning? Volcanoclastic.
No, of course not. You see, when we talk about volcanoclastic, it means that it's a mixture of both clastic sedimentary rocks and volcanic rocks. And in terms of volcanic rocks, the best example here, as we have mentioned with you, will be ash. So when we talk about ash and clastic sediment like sandstones, we call that a combined term we provided as volcanoclastic. And that is why, if you allow me to go backwards into the description of the absolute geological aging, we mentioned with you what are the lithologies that are normally going to be dealt with. So unfortunately, they mentioned here as volcanic rock, but in most cases, whatever you find here, especially for the potassium, argon, rubidium, strontium, and uranium lead techniques, they'll normally be trying to focus on zircon and micas, and also the best kind of, let's say, lithology in a sedimentary basin environment where you have fossils and sedimentary rocks will be ashes. Those ones will be the major components that will be analyzed for absolute aging techniques. So when we talk about volcanoclastic, we mean a mixture of both rocks of volcanic origin and sedimentary origin. But when we have seen here, it means that it stands for ash being intercalated between, as you can see, volcanic deposits intercalated with sedimentary successions.
Thank you.
Very good. So whenever you people will have a chance to probably do some absolute age estimates, I don't know, unfortunately in Kenya we don't have such kind of technology, but nonetheless, apart from ashes, pay attention to glauconites. Glauconites also tend to present very good results of isotope analysis. Now, on the other hand, here we have an imprint, probably a cast of a Middle Cambrian trilobite called Xistridura templetonensis, and it comes out from Australia. It's a typical representative of the so-called Cambrian fauna. And as you can see, based on your paleontological experience, can you tell me the three modes of life of any organism? How do we classify them? Once living organisms, or if you don't, once living organisms, look at them right now. How do they behave? And we have a specific group of organisms that we classify them into. Any ideas, gentlemen? Any ideas, people?
I don't know whether I can guess because I don't know, but I can make a guess.
Right.
So like now we can classify all the organisms into maybe plants, but when it comes to animals, we just divide them into two, vertebrates and invertebrates. That's my guess.
Okay, that's your kingdom, but I'm asking about mode of life, on their behavior and how they behave. I'm asking you for a specific reason because you have this kind of caste. And what will be your assumption? Because remember that paleontology normally provides us with three most important factors. First, it gives us the relative geological age, right? That's the first application of paleontology. Second, it gives us a chance to correlate, right? To compare our section with another one located at a certain distance away. And number three, it enables us to do paleo-environmental reconstruction. So when you have this kind of creature called a trilobite, Stridura templetonensis, what will be your reconstruction? How would you reconstruct? And that is why I'm asking you. Generally, all fossil organisms have been subdivided into three groups based on their mode of behavior or existence. How would you associate that with? We want to hear other people. We have been hearing Samuel too long and too much. We want to hear somebody else. Brian, Bwana Vugwi, Bwana Guy, Bwana Nyango. Are we together? Ama unalala nyinyi wote?
Yes, together, Doc. From my end, I would request if you can repeat the question because there was a break in the internet on my side.
I'm asking the mode of behavior of all fossil organisms. They are classified into three groups. How would you classify them? What are those classifications? Three groups of organisms based on their behavior. From your course of paleontology. I'm asking you this because you see, oops, what is happening? I'm asking you because we are observing with you an imprint, like I said, a cast of this trilobite. And the major functions of paleontology, it gives you correlation purposes, relative age, and depositional environmental, let's say ecological or environment reconstruction, paleo-environment reconstruction. What would you associate with this fellow? What did it do? How did it survive? Looking at this imprint, what can you suggest? Any mode of life? Bwana Aleng, are you with us?
Yes, I am with you.
Wonderful. So what is your reconstruction? What will you suggest happened? Or you have no suggestions?
I'm thinking about it.
Yeah, my friends, this is where paleontology catches up with you. Bwana Vugwi? You have
Yes, I'm with you.
Do you have anything for us?
Okay, I'm also trying to think about it.
So, in order to think about it and to have a general conclusion, remember that all organisms normally have three modes of life. We consider one group called planktonic organisms, those that do not possess their swimming apparatus and just flow after the water current, right? Wherever the tides take it, that's where it goes. Those are plankton. No other, we call them phytoplankton, zooplankton. Those are planktonic organisms. Now, those organisms that possess a swimming apparatus, meaning fins and etc., that we call nekton. And now we have the third group is those that are attached to the seabed, and that is what we call benthic organism or benthos. So you have now three groups: plankton, nekton, and benthos. According to you, this fellow called trilobite, was he a nekton, plankton, or benthic, and why? Bwana Samuel, maybe you can tell us, or somebody wants to say. I hear a guy wants to tell us something.
Again, I guess benthic because of the way it is structured.
Okay, that is your assumption. We have benthic. Anyone else with another opinion?
I think it is nekton because of the fin-like structures. Maybe it used for swimming or something like that.
Okay, now we have nekton, we have benthic. Any other ideas? Oh, that's the final. Anyway, not to torture you too much, what happened is that, yeah, I hear somebody.
Okay, because from the explanation of the benthic, they occur deep. I think the trilobite is a nekton because I don't think it can occur that deep in the water body.
Okay,
So
more or less all of you are more or less right, but then if you allow me to go back into this chart, especially this one of the Precambrian, we can also expand it a bit into the Cambrian, early Cambrian times. You can see that most of the oceans that were covering our planet at that time, as we mentioned, were quite, especially the ones that are on the shelf parts, were quite shallow, right? On the other hand, the massive development of cyanobacteria that led to the development of our stromatolites also induced a more carbonate depositional environment. And that is where our trilobites started to appear. As you can see, most of the continents, except the Gondwana, were located near the equator. And whether we like it or not, even in the geological past, everything that is associated with the equator is more or less of warm water conditions. So as you can see, we can now reconstruct and see what were the environments in which trilobites and other fellows, including mollusks, tended to thrive, were warm and shallow conditions. On the other hand, trilobites, there were fellows, as you can see, they were the first organisms that seemed to possess the so-called the head and the thorax part here, right? And apart from that, there were animals that also possessed, some of them were called opistoparia or protoparia, depending on where certain kind of sutural line was present relative to the eyes. Like in this case, we can see that this fellow might have possessed eyes, but nonetheless, most of these organisms tended to thrive within the seabed. Once again, let's don't forget that they were quite shallow within the shelf part. And the way the environment and the way the sun was very aggressive at that time, there was no ozone layer, we can assume that they were kind of blind. And what they used to do, they used to burrow at a very shallow depth in the seabed and actually used to extract some of organic matter that might have precipitated, and there were a wide development of so-called organic mats the so-called bacterial mats that are actually impeding and sealing the seabed from the initial waters of our planet. And that is what they used to thrive on. And actually, so they were just grazing animals, but animals that used to graze and burrow the shallow portion of the seabed. So that is what we can eventually call them as seabed grazers. So as you can see, the next period as we have here now takes us to the Ordovician time. And compared to the Cambrian time, if we were to look at the United States, which is once again here, Laurentia, it is experiencing some sort of anti-clockwise rotation, right? If we compare it with the Cambrian time. Again, the location is here of the Laurentia. It's separated from Baltica and Siberia by the Iapetus and the Paleotethys. As you can see now, Gondwana seem to have moved northwards towards the equator, and especially the Antarctica is now within the more warmer environment. But nonetheless, as you can see, the remaining portions of the Gondwana are once again surrounded by the seas and the waters of the Pantalassic on the other side, and the Paleotethys Sea that has started to develop between the Baltica, the Siberia, and Laurentia and Gondwana. The other organisms that thrived at that point started to develop. Okay, we have the arthropods presented by trilobites still continue. We have the brachiopods, we have the mollusks now diversifying. We have the Coelenterata or Cnidaria, which are just the corals, the ancient corals. We have some graptolites, right, quite common in the Silurian time, but they tend to have occurred in the Ordovician time. And we have the echinoderms, which are very tightly also related to the starfishes and etc. The urchins, the sea urchins, and the echinoderms are here. So as you can see, this is the kind of development that continues on. So as you might remember, the lower boundary of the Ordovician is estimated by the past occurrence over fossil called Iapetognathus fluctivagus. As you can see, Iapetognathus, I think it borrowed its name from the Iapetus Ocean. This is where it seemed to have thrived. These organisms, as I mentioned to you, conodonts, are only presented by their teeth, and the rest were just like a snake or an eel-like body. They used to swim, and this is where probably at the end of the Cambrian or even at the mid-Cambrian times and eventually into the Ordovician time, we have the first evidence of predator behavior. So we had the prey and predator relationship between the organisms involved. So as you can see, the Ordovician system has been radioisotopically dated. If you also recall, Ordovician was the last system. Remember, Ordovician is the last system to have been introduced in 1879, if I'm not wrong, by a fellow that eventually helped to solve the so-called Cambrian conflict between Sedgwick and Murchison, because each of these fellows who had introduced either the Cambrian or the other Silurian system believed that their system is more superior compared to the other, and it occupies a certain on the super their boundaries were kind of superimposing one another, and that conflict went on for quite a long time until they even died, without knowing that later on in 1879 Lapworth actually introduced the Ordovician system that finally sealed and solved the issue of the boundary between the Cambrian and the Silurian period. So as you can see, radioisotopically, it has been dated to last around 495 to around 443. But according to the latest data, that 495 has been reduced to 485 million years. In terms of the paleo environment, you can see that Ordovician rocks are found on every continent except for Indian Peninsula. That is a unique kind of situation. It has been seen throughout the globe, but India, for a certain reason that it has always been uplifted and squeezed between Australia, Africa, and Madagascar, it had no time for deposition of the Ordovician. So approximately you can see that within the Indian Peninsula, we have a hiatus or unconformity or hiatus of approximately 50 million years of no deposition on a whole entire, let's say, continent or subcontinent level. So during the Ordovician, the continental masses were widely dispersed other than the Gondwana supercontinent. The Ordovician is arguably the period of greatest marine diversification in the fossil record, and here we have the groups that appeared in the Cambrian, including bivalve mollusks and gastropods, became much more diverse and widespread. So other groups appeared and diversified for the first time. These are corals and bryozoans, which after a rare occurrence in the Tremadochian, formed diverse bioherns and even reefs. So the Great Barrier Reef that we observe with you today in Australia was very widely developed, especially in North America, in some parts of Midwest, in Texas area. That is where most of the reefal structures at that time appeared. And apart from that, we have cephalopod mollusks. And here we have the nautiloids became the major predators. As you can see, the crime, like I call it, the prime, the food chain prime, crime between the predators and the prey became very much well established by the Ordovician. We also had free floating graptolites. Trilobites continue to diversify. Brachiopods are added up with so-called articulated brachiopod fellows. And here we have the first attempt by the plants to conquer the land. But when they did that, they only occupied the very most shallow and, let's say, swamp areas not far away from the sea. That was the first attempt of the colonization of the planet by land plants. However, everything once again ended up with a big tragedy. As you might remember, paleontology does not only deal with the evolution and the development of fossil organisms, but it also deals with the tragedies and extinction events, like they're called. So at the end of the Ordovician, we had the first event of extinction that wiped out most of the organisms. And as you can see, it has been related with the glaciation. Meaning, once again, some event happened in the atmospheric level. Apart from plate tectonics, the atmosphere, it's more likely that the level of carbon dioxide, with which is now considered to be a green gas, right? Greenhouse gas effect, it reduced, and the amount of oxygen in fact increased, and that led to glaciers. Both glaciers can occur like on continents and also in marine environments. So this was the first kind of glaciation event that took place in the Phanerozoic at the end of Ordovician time. So the next period, as you can see, is now presented by Silurian. And here, once again, the Scotese map gives us a slice of 425 million years ago. And as you can see, the Paleothetis begins to close up a bit, and it's completely going to be isolated from the north by the Siberian, Kazakhstan, North China terrains. Here we have Australia, and parts of Antarctica are still occupying the let's say, tropical part of our or planet. However, the remaining parts of Africa and the continents here are actually, the Gondwana is at the further south, and this is where the glacial events actually took place. And it was quite a prolonged term and prolonged glacial events. If you allow me, may I ask you what is the product of glacial activity? What product will we as geologists observe? What will be the sediment that will be generated by glaciers? How do we call it?
Moraines.
Well, moraines are once again glaciers. The moraines are just long, let's say, tongues of ice that are moving through a certain slope. But of course, they are called moraine deposits, but we will eventually get something called, you've probably heard about tealites. Tealites are the products of this glacial on continental or land glaciations will generate something called tealites. So tealites are ones that have been observed in some parts of Africa. But the first tealites that are actually observed here in Kenya are of Carboniferous age, and they have been discovered within the Lamu Basin, within the northern part of the Lamu Basin, within the so-called Mid-Galana area. So once again, if we look at the organisms that thrived at this particular time, we have early land plants, as mentioned, the attempt. Then we have, it's been illustrated here, scorpions, we have cephalopods, we have the jawless fish, as you can see, first indication. Actually, we as human beings are vertebrates, right? And our ancestor, the major ancestor, of course, is fish. And as you can see, at around the Silurian time, we have the first fishes appearing. Then we have the sea scorpions and we have the crinoids, which actually developed. These are attached organisms, but of course they had their calyxes that used to detach and used to swim around like a plankton, but nonetheless, most of the crinoids were of benthic origin. As you can see, there is a certain kind of crisis in the Silurian after the end of Ordovician extinction event, and it really required some time. And if we look at the duration of the Silurian time, approximately 25 million years, the first couple of million of years related with Silurian were the time of recovery. And as you can see, the events still are felt by the glacial activity and the cold environment. It's only when the warming up of the atmosphere occurred, that is when more diversification of organisms started to occur. So the Silurian system here we can see is radioisotopically dated to have lasted between 443 to 418. It follows the Ordovician time and is immediately overlain by the Devonian. The Silurian forms the latest part of the lower Paleozoic and is subdivided into 4 standard series, quite important to remember. So the lowest Silurian is known, or the series is known as Landoveri. It ranged from 443 to 429. That is followed by Wenlock from 429 to 424. Then we have Ludlow in 424 to 420, and Pridolia, or Prigidolia at times it's called. It ranged from 420 to 418. Apart from Landoveri and Wenlockian, and Ludlow, Prigidoli is identical. These all epochs are widely, or series are widely examined in UK. In United Kingdom, while Prigidoli is actually been identified as a section point area in the Czech Republic in Central Europe. Now, in terms of paleoenvironment, the Silurian geography was dominated by a vast supercontinent called Gondwana, as we had seen previously. which included today's South America, Africa, Peninsula, India, Antarctica, Australasia, as well as adjacent terrains of Southern Europe and Middle and Far East. Other substantial terrains were Laurentia, which included most of North America, Greenland, and eastern part of Siberia, and Baltica, Avalonian. This is mostly of northern and western part of Europe. The oceans were dominated by the vast Pantalassic Ocean, which was comparable to the size of today's Pacific, while the Iapetus Ocean that was found between Laurentia and Avalonia had been very substantial in Cambrian and Ordovician times, was steadily closing. So what does that mean? It means that here as the Pantalassic Ocean, if we go backwards again, I don't seem to see it. Where is the indication here? I mean not the Pantalassic, but the Iapetus Ocean here has been experiencing several subduction zones, and the oceanic, paleoceanic crust eventually was consumed into the internal part of our lithosphere. And it eventually led to its closure and the collision between Laurentia, probably, and part of Gondwana. So as you can see, the Iapetus Ocean between Laurentia and Avalonia, Baltica started to close down due to the subduction processes. Right, so organic world of the Silurian, the benthos, was dominated by brachiopods, bivalves, gastropods, corals, stromatoporoids, bryozoans, echinoderms, calcareous algae, and trilobites. Plankton includes cephalopods, which actually had possibilities to swim or follow the water currents. You had also free-swimming graptolites and a variety of various kind of microplanktonic organisms such as acritarchs. In fact, acritarchs have their first occurrence within the Precambrian times, especially quite common in the mid and late Proterozoic times. We have the chtinozoans and we have spores, which were probably spores themselves were probably extracted by those higher plants that conquered the land by the Ordovician. Now, the ostracods and conodonts were certainly mobile and in some cases dispersed quickly, but their detailed ecologies and modes of life are less certain. Now, on the other hand, Silurian, just like the previous Ordovician, became the time when fishes became progressively abundant. Yes, Samuel?
Yeah, my question is, now that we are saying crinoids were the particular ones of echinoderms, what gives them preference against the other, what do you call the other part of the echinoderms? The
crinoids, echinoderms.
Because there are two parts. The echinoderms are crinoids and the other one. I don't remember the other name, but it's there. I can visualize it. What gave this one preference? The crinoids.
Well, as you can see, well, do we have the crinoids here? Crinoid there, it's more likely that they are now experiencing some. Nonetheless, as you can see, we have the echinoderms, particularly the crinoids, who are now becoming the most dominant one, is because probably what had happened is that it started to warm up And the crinoidea and the starfishes, especially the starfishes that are present here, eventually indicates a more warmer environment, more carbonate depositional environment. And on the other hand, we have echinoids. Echinoids will once again prefer an, let's say, sedentary mode of life, while the crinoids will be more of the group that are more mobile now. So that means that they had to kind of change their mode of life and probably even migrate on a certain distance away compared to the echinoids, which were more attached to the seabed. So once again, it's a good question, but it once again shows that the environment probably now enabled them to kind of occupy a more broader niche, and that meant that they had to kind of migrate on a larger distance away from their zone of comfort, which was quite a shallow marine environment. So nonetheless, it means that they had to change their mode of life. So probably changing their mode of life from benthic attached life to more of a planktonic nature.
Thank you.
Karibu. So here, as you can see, we have the first, like our first ancestor, let's say the fish, which gave life, start to vertebrate organisms. This is the type of primitive fish that was first developed, as you can see, but nonetheless, it did possess the head, the thorax, the eyes, and the fins were quite well developed. And again, they also possessed what really differs them, that they had a chance, the gills, right? They were able to kind of swim even into the deeper portion of the oceans at that time, and eventually extract oxygen from the water through the system of the gills. The next kind of period that follows now, the Silurian time, is the Devonian. And as you can see here, we have the Iapetus Sea has completely disappeared. And this is when we can see that all the continental blocks are now once again amalgamating, or the start of the amalgamation, which actually peaked during the Permian time, where we had the Super Gondwana continent now, or the Pangaea, let's call it, completely combined and uplifted. As you can see, the Rake Ocean is still present between the Laurentia, which is now called Euro-America, and the Gondwana. It is quite of a tropical nature. It's quite warm, and the continuation of various kind of shallow sea deposition, especially carbonates, continue in these shelful parts of Gondwana and in parts of Laurasia, let's call it as well. What else? Siberia continues to migrate northwards and wobble around. Pay attention to, if we are to look at the Laurentia, the anti-clockwise rotation of the Northern American block continues, and US more or less of the Laurentia continues to actually occupy the current kind of position, geographical position of the East and West. Major organisms here, you can see we have some development. Let me just increase. Right, so we have ferns. These are the first kind of ancestors of the ferns develop here. So it means that more and more of the land masses have started to be being occupied by land higher plants. And to go a bit ahead, as you can see, the next period we know is the Carboniferous, which actually ended up by generating massive kind of coal deposits, especially in Europe, in Northern Hemisphere, and some portions of even in South Africa. We're related with the Karoo Formation. Just going a bit ahead, this was a time when more and more higher plants started to thrive within the continental mass. Then we have the cephalopods, some early, of course, as the trees, the higher plants continue to develop, and the next kind of slides will actually show what kind of high plants these are. These are ginkgos trees, which actually reached approximately 30 meters in their height, just resembling the current high trees that we observe today of the eucalyptus family of that same height. So once this kind of development of higher plants occurred on the continents, this immediately attracted the attention and eventually the evolution of insects. And insects were the early insects actually appear in the Devonian. And these are normally flies, dragonflies, cockroaches, all of these fellows tended to have followed the forests. Apart from that, in the warm seas of the Reich Ocean and some portions of the Pantalassic Ocean that still continues to thrive on the other side of the globe, as you can see, the amalgamation of continents on one side meant that the whole entire other part of the globe was occupied by the water masses. And that is where we have the sharks that thrived here. And this was the first time where we have the appearance of bony fishes that becoming quite dominant at this particular time. In fact, Devonian has another time that this is the period of the fishes. And apart from the fishes, we have another vertebrate organism that now tends to thrive, and we have the first early amphibians occupy the continental, the transition between the continental and marine environment, and especially within the lagoonal areas was a time where these fellows tended to thrive. If we were to look, into the chart itself, the Devonian, almost all, and actually all of their stages are actually characterized by the global sections stratigraphic points, GSSPs, and these are their numerical ages that have been based on the absolute isotope aging techniques. Right, what is happening now? Right, so the Devonian period of the Paleozoic era was only slightly shorter than the entire Cenozoic era where we are living right now. Currently, the Cenozoic era has around approximately 65 or 66 million years. The Devonian, as you can see, occupied the whole entire duration of the Cenozoic era as we know it. Now, this was the time of the many fasts in the early Earth history, and it's normally known to have the switch of the planet switching from the hot greenhouse state to a cold icehouse phase, and that has been termed as the so-called Hangenberg bio-event. The Devonian is named after fossiliferous marine strata exposed in Devonshire in southwest England, and it was some period that was introduced, as I mentioned to you, these were initial when they were buddies, by Adam Sedgwick and Roderick Murchison in 1839. Also recall that Adam Sedgwick introduced the Cambrian. I think, no, the other way around. Murchison introduced the Cambrian, while the Silurian was introduced by Sedgwick. And that was also the event that led to their becoming from friends to frenemies. In terms of paleoenvironment, the Devonian saw the explosive diversification of vertebrate life, especially new species that proliferated both in marine and freshwater environments. So we have both lacustrine, let's say, and marine fishes. And this also includes the first paleontologically confirmed case where we had now the terrestrial vertebrates that, as you can see, the first are the forests that went to conquer the land. Then after that, insects, and after insects come the vertebrates presented by amphibians that migrated from water, shallow water, and at times when they wanted to take a sunbath, they actually walked out into and traversed through the landscapes. In fact, by this time, if we look that the land has been occupied by the trees, I think it now becomes quite vital and clear why trees are very much important. It's because it's believed that trees are the ones that now created through the processes of photosynthesis an extra atom of oxygen, and as you know from chemistry, oxygen 3 is nothing else but the ozone. So that is where now the earth started to breathe more, and these processes of photosynthesis led to the development of a thicker ozone layer that prevented from the ultraviolet harmful rays of the sun. And eventually that led to now the amphibians exploiting the nearshore landscapes. So as you can see, both plant and animal groups were rapidly evolving and invading the terrestrial realm. And in the Devonian, the Earth's first forest evolved with trees that now towered some 30 meters in their height. In fact, the next slide will actually show us the reconstruction of these ginkgo, sigillaria, huge trees that eventually later on in the Carboniferous became the major material for the coal beds. And here is how the Devonian first forest trees looked like. And as you can see on the landscape, you have a millipede that eventually is a huge kind of, just resembles the insect that now, or the arthropod that followed the development of this first forests. On the other hand, we have this fellow, the amphibian, first amphibian, and it has been called the Tiktaalik rosé. This is one of the examples of an amphibian and its reconstruction based on its fossil remains. As you can see, this fossil, it did not really possess like the true legs that amphibians had later on in the Carboniferous and Permian times, but nonetheless it could crawl around, have a sunbath immediately, and run away back into the marine environment. So this time is followed. The next one is also a very crucial time, and as you can see, we have the Carboniferous. Be aware that the Carboniferous is normally subdivided right now into two, let's say, a series or epochs. We have the early Carboniferous that is called the Mississippian, and the following next one is called the Pennsylvanian. As you can see, in terms of GSSPs, the global stratigraphy section point, not all of them have been dated so far based on both the biostratigraphy and isotope studies. Nonetheless, as you can see, it led to the amalgamation and the rotation, further rotation. As you can see, the US is continuing the counterclockwise rotation. The Rake Sea seems to disappear between Laurentia or Euro-America, like it's called here, and some parts of the Gondwana. You can see that Africa is now occupying almost the kind of position it occupies today. Paleotethys Ocean is still quite broad, and the rest of the Pantalassic Depression, as we know, it has been like current Pacific Ocean still remains open up till present. The other kind of event that is widely seen even at this chart, we can see a massive glaciation event happening in the southern part of the Gondwana, and it actually occupied some parts of Brazil, Argentina. Here we have South Africa, Namibia, Angola, and also Mozambique, and some parts of Kenya were also affected by these glacial activities and events. And this is where, in fact, Kenya is located here. This is where, in the Lamu Basin, which is actually located here, we have the first traces of the deposition of our sedimentary rock units that start with the so-called Taru Formation, which is also believed, especially the lowest portion of it, is believed to be presented by Tillites. and has been placed somewhere here between the Mississippian and Pennsylvanian series. In terms of the organic world at that time, as you can see, if we are to expand, we can see we have giant club moss trees, the ginkgo probably as a family. We have the crinoids, we have the amphibians, we have the lobe-finned bony fish, and we have the bryozoans. So nonetheless, especially the bryozoans and some parts of the crinoids, they normally developed within this equatorial seas, the Paleotethys Sea and the Rheic Sea that existed between the Euramerica and the Gondwana. But generally, if we look at the southern portion of our globe, it was experiencing the initial stages of glaciation. So Carboniferous, just like the previous Devonian time, had a long-lasting span of around 60 million years, was an important period in the Earth's history with the major changes in the atmospheric composition in terms of both oxygen and carbon dioxide, and the development of ice worldwide, and the formation of vast tropical peat coal deposits, and the radiation of plants and animals on land. Carboniferous was introduced by two Williams. One was Conibri and the other one was Phillips in 1822, who based their work in northern England, actually closer to Scotland. From their studies, particularly in Yorkshire, they recognized the distinctive coal-bearing sequence that had an important limestone sequence below it. So the base of the Carboniferous system, also known as the Tournesian stage, has now been formally defined as the first occurrence of another conodont, not Iapetognathus fluctuagus, but by this time, who can volunteer to pronounce this? I'm leaving up to you people, future lecturers of stratigraphy and paleontology. Who can try to pronounce that fellow, the conodont again? Early volunteers? Yes.
Which one particularly?
The one who could the first one.
Are you saying the Seiphonodella?
Yeah.
Oh, Seiphonodella sulcata.
Exactly. And now to make life easier, the base of the Permian, the next system, is now identified by the first occurrence of the next conodont, which has the name of Samuel Maliza too.
Streptognathodas lobensis is very difficult.
So you start with Siphonodelus sulcata. People, this is a matter of memory. You must know it by all means. And the next one is Streptognathodus iwabawensis. That is the complete name. So we have two conodonts. Siphonodelus sulcata, that is actually determined at the base of the lithological change from the probably marine carbonates and the overlying now coal deposits presented by various kind of coal deposits of the Carboniferous, Siphonodelus sulcata and Streptognathodus iwabawensis. So if we were to look, yes.
Excuse me, does it mean that when you see those two, you realize that there was coal?
Yeah, sure. The Tournesian stage, as you can see itself, the term Carboniferous is already indicating that the lithological, it was the first kind of lithostratigraphical, let's say, before the Cretaceous, it was the first kind of period that was named based on the composition of the strata that is presented. And that is why instead of calling it coaliferous, they called it Carboniferous based on the majority composition presented by fossil carbon. And that is how it turned out to be Carboniferous.
Thank you.
The next lithostratigraphical period also selected based on comes from the Latin name and French name standing for chalk. So instead of the British used to call it chalk for a long while until I think the early or the late 19th century, but initially they used to call it chalk or Cretacea or Cretaca based on the Latin composition. So if we were to look on the paleo environment, we see that the Carboniferous saw the gradual accretion of many continental land masses as seen in the chart previously. At the beginning of the Mississippian, 2 or 3 major continents had formed. First, Europe, North America, had collided and generated the Euramerica, and which was later on been termed as Laurasia or Laurussia. Now, accretion continued and led to the collision of when 2 continents collide. Of course, they close everything that was there in between. And in this case, the Rheic Ocean, just after the Iapetus Ocean, became the next victim of its closure. And in some cases, the process can be different. You see, once again, answering the question that Samuel asked us at the very start, when we have the convergent plate boundary, when 2 blocks are colliding, it also depends what kind of blocks are colliding, because you may have, on one hand, you may have the continental crust colliding with the oceanic crust, and that will eventually lead to the subduction of the more heavier, denser oceanic crust beneath the continental, and that's how it will close. In case if we have a collision of 2 continental crusts, of course we'll have an uplift, and eventually the generation, like a good example, like here we have a Appalachian mountain belt, but in the most recent one has been the collision of the Indian subcontinent with the Eurasia and the generation of the Himalaya mountains. On the other hand, we can also have a situation when 2 oceanic plates collide, and then one of them, of course, once again will subduct and another one will kind of abduct or go above it. So there are various scenarios of this kind of collisions, and depending on the oceanic crust that collides, I mean the type of crust that collides. So as you can see, many of the southern continents formed the supercontinent we know as Gondwana. And in the Carboniferous, there continued to be continental accretion, for example, South America. Through the Carboniferous, the northern and southern continents continued to amalgamate, and by the Permian, the giant supercontinent Pangaea had been formed. And now, looking again on a quick question, what do you think happened once an amalgamation of us, this supercontinent Pangaea, occurred, where all the continental crust and all these masses actually amalgamated into one body? What do you think that led to? It actually is been an explanation is provided. Well, it normally provides the change from more of ocean, let's say marine environment, into a more continental environment, and that led to the change, the major climate change with tropical drying and the spread of continental red beds, which is an indication of oxidation and weathering, massive chemical and physical weathering. On the other hand, we had the decrease in rainfall prevented peat formation in more tropical areas and was accompanied by the apparent extinctions of many terrestrial plant and animal groups. And that led to a massive extinction event, especially in the Permian Triassic time, when almost 90% of organisms were wiped out. It is considered as the largest tragedy that the biota, or the biological, both fauna and flora, had experienced in the history of our planet. Right, and here are some of the reconstructions, paleotectonic and paleobiogeographic reconstructions for late Carboniferous, and you can see we have all these angiosperms and other kind of so-called higher plant organisms thrive, and especially within the tropical and subtropical area. Then we have the cool and Arctic, and we have the warm, temperate faunal groups, as you can see, and surprisingly, the warmer ones were located in the northern hemisphere within the Siberian Craton and some parts of the China Craton. In US and in Europe, in northwestern Europe, we had this group of tropical and wet group of faunal trees, like you have the pteridosperms, lycopods, tree ferns, chordaids, and sphenopsides are the ones that dominated in this environment. On the other hand, here, if we were to look at Kenya and the other part of East Africa, as you can see, they were all under the ice sheet and they were under glacial environment. So in most cases, as you can see, the cold environment was most likely developing within the Sahara, actually within the tropical part, but there are some portions of trees, the so-called cool Arctic type of pteridosperms and chordaids and sphenopsides that thrived within the central part of Africa. And you can see they occupy parts of Sudan, going to Chad, and going afterwards to Nigeria, to Cameroon, and the Central African Republic. That is where we are likely to observe some amount of coal deposits as well. It's more likely that they might have occurred there. But due to the processes of various kind of local tectonics, of course, erosion is something that might have swept it all away. But this is once again an attempt of a biogeographical reconstruction for the late Carboniferous, which we also know as the Pennsylvanian time. So in general, as you can see, if we were to reconstruct the Gondwana or the Pangea, as you can see, all of it combined together, we have several belts of various kind of fossil trees, of fossil fauna, of fossil flora that developed, and the one at the south was known as the Glossopteris group, the one at the equator was known as the Gondwanian, and the one at the northern, especially in the Siberian part, was known as the Angaran group of flora. So if we were to look on the organic world of the Carboniferous, we will see that there is a major radiation in many groups of vascular plant plants, and among them we have the spore-bearing plants, the lycopsids. They went major radiation into several new ecological niches. Warm shallow seas supported a rich benthos that was dominated by brachiopods and crinoids. And it's also known for plankton diversity. Appears to be low, with the fauna dominated in few groups. First and foremost, these are acritarchs, the marine aquatic algae. In some areas, reefs dominated by rugose and tabulator corals, which unfortunately perished at the end of the Permian time. And the current ones are the only ones that we know belonging to the other group, the third group, the Scleractinia group of corals. The other thing is that they, together with sponges and bryozoans and calcareous algae, were very important, for they generated the most known, once again in the Midwest, especially in Northern America, coral reef structures, which eventually turned up to be potential oil and gas structures, reef structures. Apart from that, in the Carboniferous, foraminiferous were characterized by so-called diffusulina that became quite important. Nectonic organisms, the ones that managed to swim by their own swimming apparatuses, were presented by goniatids or goniatites. We have also the vertebrate conodons. Fishes also found in many marine and non-marine environments. A variety of sharks are known in the Carboniferous deposits, and some of the best examples are the Stetacanthus in Scotland, and from the ones that normally developed within brackish marine environments. On the other hand, we also had ray fishes and lobe-finned fishes also became diversified in the oceans at that time. So that is how the Carboniferous looked like, apart from some extinction events that were seen before. It is known for its diversification, and especially it concerns some of the invertebrates, but it also deals with expansion of the niches of various kinds of fishes, including ray and lobe-finned fishes. So we progress on to the next epoch of the Carboniferous, known as the Pennsylvanian, and as you can see, the rotation counterclockwise continues on. Here we have we have another global stratotype section point for the lower boundary. It's normally taken by the first appearance of another conodont this time around, the ones that actually is placed here with the key. And it occurs in South Nevada in the United States, in the so-called top of the Battleship Wash Formation, and it is presented by the Declinognathodus nodiliferus sensu lata. That is what determines the lower boundary of the Pennsylvanian upper or late Carboniferous epoch. As we see from the Scott 6 million, we see the amalgamation of this super Pangea taking place, or taking a pace. Most of the Gondwana still continues to be covered by glacial activities, especially in the Antarctic, in most part of Africa, as you can see. The only part of Africa that was quite warm at this time was North Africa, in the Algerian and Moroccan part that was completely amalgamated with Northern America and some portions of Europe. And the warm environment was observed within the Paleothetis that still continued to thrive between the Siberian, the Eurasian, and some part of the, let's say, North China and some of the South China terrains presented here. But the southern pole continued to be a very cold environment. Now, in terms of the life forms, we continue to see chordaceous trees. We also see the early reptiles that now seem to have experienced an evolution from the early amphibians, and now reptiles and amphibians are a bit separate group. Reptiles now kind of roam more into the interior, continental interior. As you can see, we have a huge dragonfly that continue to develop here within the dense forests that continue to thrive in the tropical part of the Gondwana, of the Pangea area. Apart from that, we have the Acantodian group of fishes, and we also have the other Chondricholon type of fishes and amphibians. It's actually a mixture between a fish and an amphibian. And here is actually the life of the Carboniferous, as you can see in the tropical part. You see these large dragonflies and these huge trees that even will take a height of more than 30 meters. And there's an amphibia, and there's another kind of group of creatures that share this kind of, almost like a conodont probably, but I'm not sure this is a conodont. I don't know what this exactly stands for. But nonetheless, as you can see, there's a well-known fellow called Ichthyostega. He's an amphibian whose remains have been found in Brasilia, in Africa, especially in South Africa, in Namibia and Angola area, and also in Australia and in India. And that was one of the organisms that was used by Alfred Wegener to come up with his new plate tectonic theory and kind of combine the Gondwana and the Pangea reconstruction with his ideas of once solid or united plate. It seems I've been thrown out. There's a network issue. Hello?
You are audible.
I'm audible. Okay, great, because I'm seeing that I've lost my network connection. So anyway, as you can see, the almost through. Just a second.
Welcome back.
Yeah, asante. Yeah, we are back in our Carboniferous time, and there were some attempts made in Germany, especially within the Ruhr, Gebiet Basin and others. And here we have the example of the Steinkohlen formation, the Germans trying to make some understanding of the coal basin developed within the Ruhr Basin in Western Germany. And here we have sphenopsides became quite abundant. And here we have the so-called archaeal calamites. And here's an example, I think one of them that became quite more or less the dominant. Now, to make things easier, the Carboniferous was once known as the age of ferns. And the most advanced plants of the late Carboniferous were the closely related chordaites and the conifers. So that is where the conifers actually start or begin their journey. These are the higher chordaites. This is the way they have been represented. And here, as you can see, here are the lower fern group of trees and plants that became quite dominant, especially in the Pennsylvanian time. We finally enter into the Permian period, and this is the last period of the Paleozoic. And actually, as you can see, it continued with the same process of amalgamation of the Pangea on the collision and the closure eventually of the Retic and the other seas. Siberia also started to kind of converge together with the Northern American territory. North America continued its counterclockwise rotation. We can also see that this is a time when the conifers continued to dominate, and that led to the development of various kinds of forests. But additionally, we also have cockroaches, amphibians, bony fishes, and herbivorous synapsids. The synapsids are actually, together with the other carnivorous synapsids, became the ancestors of the dinosaurs that actually appeared later on in the Mesozoic time. If we're looking at the geological timescale, we can see that most of the periods, or the stages of the Permian period have their GSSPs firmly confirmed. However, the only issues are still observed within the Artinskian and the Kungurian times of the stages. The other thing that we can notice here is that it seems that during the Permian now, the glacial events that were very much common in the southern part of Gondwana have started to retreat, and that retreat led to the formation of various kind of lacustrine and fluvial lacustrine and deltaic kind of deposits within this internal part of the continents. But as you can see, in most cases, the whole entire Gondwana is quite solidly merged together with Australia, Antarctica, India, Madagascar, Seychelles are here. Well, Malaya and South China and North China are still independently rotating within the northern and southern or equatorial parts of the Paleo-Tethys Ocean. So the Permian period that spans now for a shorter term compared to the Carboniferous had only around 43 million years, and it spanned, if our current estimates, around 298.9 to 251. This is a bit of outdated. Witnessed several major turning points in the Earth's history. Pangaea, the greatest supercontinent of all time, finally amalgamated in the Permian and began to break up again, almost immediately in a prolonged disintegration that would finally be completed by the Cretaceous time in the Mesozoic. The end of the Middle Permian was marked by another extinction crisis that primarily affected the inhabitants of the shallow tropical seas. This was the first such crisis since the end of the Devonian 100 million years previously. Much worse was to follow at the end of the Permian mass extinction, by far the biggest disaster of all history of life, that actually, as I mentioned earlier, wiped up almost 90% of life on our planet. And it actually started with the era of the so-called, let's say, Mesozoic era is known as the reptiloid era. That is when the reptiles became the dominating group of organisms. Of course, that also did not last forever, and it ended up in the end of the Cretaceous and the start of the Paleogene, with the Cretaceous tertiary boundary, when the meteorite swept it off. And now, since the start of the Cenozoic, we have now the mammal era. We as humans are mammals, we all fit into that group. So here is another kind of Permian period fellow, an amphibian called the Dimetrodon. And it looks like a dragonfly, no, let's say not a dragonfly, but a dragon that can also has a spine. And its descendants is, I think it's the Comoros dragons that we see today, very nasty fellows. If they bite you, you're doomed, you're gone. And that's what they did from these fellows in the past. And whoever was not careful enough was bitten, and the bite had some kind of infectious disease immediately that affected the nervous system of their prey. So that is how the kind of Permian period ended up. And the next time when we meet with you, or probably let's give some account to the first at least period, is the Triassic period of the Mesozoic era. And this is, as you can see from the fellows, of the reptiloids. And here we have the first kind of, is it called the prosauropod dinosaur, the ones that used 4 legs of theirs to actually to migrate. Then we have the theropod dinosaurs that was a bipedal type of a dinosaur. This was a time when actually the first mammal was actually observed, believe it or not. But a bit later on, I'll show you the ancestor of all the mammals is a mouse that actually kind of sneaked in and was running between these huge giants. The trees were presented by lycopsids, then the cycads were also developed. This was also a time when the ancestors' whales, or let's say not really whales, but the so-called ichthyosaurs that actually dominated the marine environment were present. And whether we like it or not, but together with mammals, we have the first crocodile group together with the turtles appear in the Triassic time. Now, compared with the Permian time, they are much less well understood, because the Triassic, as far as we can see on a global scale, was mostly presented by terrestrial sediments, sedimentation, lacustrine, fluvial, let's say alluvial kind of deposits. And these terrestrial environments are quite known for their low preservation of various kind of fossil remains, and that is why there is a bit of a challenge here in the Triassic time. Nonetheless, as you can see, the Paleo-Tethys eventually starts closing up all around Siberia and the Ural on the northern and some the northern China. Probably plates collided. Pangea continues on, although as we have seen on the previous slide, the Pangea started to disintegrate, and that eventually means, first and foremost, of course, it's the disintegration of Australia from Antarctica and Antarctica from India, and Africa is the process that eventually began in the Triassic time. So the name Triassic actually comes out from the introduction by German geologist called Friedrich August von Alberti in 1834. And he originally recognized them in Germany in the area called as the Bunter, Muschelkalk, and the Cooper formations. The rocks of the Triassic age range from 200 to 251 million years, are recognized on all continents, and most are sedimentary rocks consisting dominantly of shallow water carbonates, mainly of shelf origin, and siliclastic red beds of non-marine origin. The global stratotype section point has been defined for the Triassic timescale, and if we look at the first stage, it's called not Indian but Induan stage, and it is based on a chronodont, once again, first occurrence. This datum defines the base of the Triassic system within the stratotype section point at the Meishan in South China. Luckily for you, this fellow did not have, or I did not have much information about, although we know with you for the name, it doesn't have a name. So we just know that it's based on a chronodont, and it has been discovered in the stratotype section in Meishan in southern China. Now, in terms of paleoenvironment, the onset of the Triassic is the world's continents were assembled into the single supercontinent Pangea, and the rest of the world was still occupied by the Panthalassa or the Panthalassic Ocean, with a westward extending arm called the Tethys. Yep, somebody raised their hand.
Yes, I'm asking. I'm wondering how did these animals survive up to date? The what do you call it? There is an insect that you showed us, and then the cockroach.
Yeah, how did they survive?
Yeah, did they reappear? Because they can't survive all those extinctions, and they didn't even have the...
Well, it's a matter of evolution. You know, like Charles Darwin once mentioned, it's not the strongest species that survives. It's the species that is more likely to adapt to the new conditions that will likely survive. So what happened here is probably, apart from evolution, we have another kind of parameter called adaptation. So whether you like it or not, like currently we also have at our department an institute called the Institute of Climate Change and Adaptation. You have to adapt, right? In order to survive, you have to adapt, and you have to kind of play according to the new rules. So what happened to this, even insects and so on, they just needed to dig deeper. Some of them probably either dug themselves, either some of them dug into their bodies into the crusts of the trees. Some of them hid somewhere, right, under the thick leaves. Those are the kind of adaptation skills that each of these organisms eventually needed to thrive through. But on the other hand, as you can see, every single time we have an extinction event, that after a certain period of time, we have a certain new organism that appears and gives a new threshold and new drive. Like, for instance, we know that in the previous Permian time, we had the diversification of the reptiloids. And as you can see, even though some of them or most of them perished during the end of the Permian time, it nonetheless gives the survivors a chance to diversify and adapt to that condition and eventually kind of transform or bifurcate and evolve into a new group of reptiles as we know with you as dinosaurs. So, and on the other hand, it also gave rise to mammals, as we are going to see later on with a couple of slides ahead. We will see the first kind of mammal presented by a mouse that eventually managed to survive and actually give life to all the mammals that we know today. So believe it or not, but that is the information we obtained from the so-called fossil record and also the stratigraphic record, which is not perfect, but nonetheless, if you kind of trace and combine the linkages, you are likely to reconstruct this kind of trends of evolution.
Thank you.
Karibu. So as we can see here in terms of the organic world, we have the pelmatozoans, brachiopods, bryozoans, but mollusks dominated the Triassic seas. And in most cases, those were the ammonites, cephalopods. We also have thin-shelled bivalves, and here are some of the Clararia, Daonella, Halobia, Monotis. I think from the course that you have been given, I think Monotis is the one that we have been mentioning so far. Brachiopods, bryozoans, and crinoids did not suffer total extinction at the Permian-Triassic boundary. As you can see, those fellows that managed to remain in the marine environment, and once again, as you can see, the sea and the water helped them to survive and preserve them, although their numbers were greatly reduced. In the Middle Triassic time, Permian-type reef communities were re-established again. So this means that after that Permian-Triassic extinction event, the conditions once again warmed up. Again, the concentration of carbon dioxide in the atmosphere probably induced the appearances of new and the diversification of various kind of organisms, including bryozoans, calciosponges, and calcareous algae. In the Carnian-Norian marine extinction event was followed by a rapid turnover of the reef-building organisms, so that Norian reefs were now characterized by abundant scleractinian corals. Remember that the previous one, the two groups, kindly remind me the two groups, the rugosa, right, and the other group of corals were eventually became extinct at this particular moment. And from there on, this turnover gave the rise to the scleractinia group, or the tabulata and the rugosa perished, but the scleractinia appeared. Now, fishes went another diversification during the Triassic, and new kinds of actinopterygians, lungfishes, hypodontid sharks, and coelacanths appeared. Conodonts, which we used with you for the subdivision of the Carboniferous and the other Ordovician Silurian times, eventually perished at this time. Regarded by many now as primitive fish group, who are relatively unaffected by the end Permian extinction time, but they will eventually disappear later on at the end of the Triassic. So as you can see, evolution is a matter of adaptation. If you adapt to the new condition, you will thrive. But if not, then too bad for you, you will perish.
Do we have some examples of Triassic in Kenya?
Yeah, we do have in Lamu, starting as I mentioned to you. Well, we'll start with the Carboniferous, going to the early Permian. Let's say that belongs to the Taru Formation. Then from the mid-Permian to the early Triassic, we had the Magie Chumvi. So the Triassic itself is now the Mariakani Formation in terms of the Lamu Basin. We'll have a separate discussion about all of these geological periods in an example of Kenya. In fact, if some of you are having any information from the neighboring countries, you're more more likely welcome to make your presentation of your findings of the kind of geological formations developed in the neighboring countries.
Thank you.
Yeah, and if we go further on, here we have now the so-called carbon film of a Triassic plant called Dictroidium, and it's quite frequently mentioned in the literature. You'll likely find this is how it looked like due to the process of carbonization, that is one of the preservation mechanisms, it has been preserved as a carbon film. Dictroidium. Yeah, and the Triassic tetrapod, whether you like it, we have Lystrosaurus murray. Lystrosaurus murray. Looks like a dog, but a very nasty one. Right, and here, as you can see, this is once again another kind of chart showing the one of the ideas that helped Wagner to come up with his Gondwana reconstruction and come up with the so-called migration of the continents. And as you can see here, we have the Cynognathus, a Triassic land reptile that was seen not only in Brazil and some parts of Peru, Bolivia, and going into Congo. From then we have the fossil evidence of Lystrosaurus coming from actually Congo, even in Tanzania, neighboring Madagascar, in India, and Antarctica, they have been found. This fellow is now the Glossopteris, that once again had such a kind of a belt of distribution. And finally, we have the fossil remains of freshwater Mesosaurus that is seen in South America and in South Africa. So this, as you can see, fossil remains now enabled Wagner to come up with his migration of these plates, and come up with the first ideas that led to the development of plate tectonics, but based on faunal remains, faunal and floristic remains. So as you can see, the power of paleontology, which unfortunately students don't like, actually gives a better clue and better understanding of what we are dealing with. Right, so I guess for today it will be more than enough to have such a kind of an excursion. If does anyone have any burning question related to the time we have considered from the Precambrian and ending up with the Triassic time, next time when we'll meet, we'll end up with the Jurassic up to the Quaternary time. And from there onwards, we'll now start introducing ourselves with the various kind of concepts of lithostratigraphy. We'll also talk about, we'll start with lithostratigraphy, go with biostratigraphy. Then, if memory does not let me down, we'll talk about facies analysis. And then as we'll proceed on, we'll also give some credit to chemostratigraphy. Magnetostratigraphy will be given a separate discussion. And finally, we'll be also talking about the various applications where stratigraphy plays a crucial role. And then probably, if time will allow us, we'll also give some credit to the Precambrian more, and by giving a Precambrian and also the Phanerozoic more larger discussion, I think we'll just scroll through the whole entire geology of Kenya, and by that we'll now better understand what are the distributions, what are the events. And apart from that, then I'll probably start, depending on how your timetable will go, we will probably ask Mr. Peter to tell us when exactly he will be more confident and it will be more convenient for him to come to Kenya, because I want us to do some practicals physically, because you have some challenges of doing it online. So in order to avoid that, when can you avail yourself so that we have our practicals on that behalf? Any ideas?
For me, I think it would be convenient if I go 2 weeks before the exams and then I stay throughout that period instead of going and then coming back.
Yeah, so that is why I wanted us to do our practicals physically. So does anyone, who is your prefect of your group, do you have an idea when your exams are starting? Is it somewhere in June? Pardon? In June. Okay, so maybe somewhere at the end of May, end of next month, we can have, like a week before the exams, we can have a physical meeting, and that is when I'll start giving you and surrendering you some notes and some practicals which we can test all these theories and so on, etc., if you don't mind. So, but by that time we'll have more broader discussion and a larger scope related to all the stratigraphical applications and stratigraphical type of analysis and their classifications. So having said that, does anyone have any burning question related to the topic, broad topic that we had so far?
Just appreciating, it was very interesting.
Okay, karibu sana. As you can see, things can bring, I'm trying to bring love from your side to paleontology, the one that you, unfortunately, it has been left without attention. So I guess with this same kind of spirit, you now understand the importance of fossils, of paleontology, of stratigraphy. But also remember that whatever we are discussing so far relates to the strata that has some fossil remains in it. But we'll also give some credit to those parts of the stratigraphy, especially the Precambrian part, that do not possess any kind of fossil remains, and the major technique used for their classification would be isotope analysis and lithostratigraphic analysis. So having said that in mind, let us meet each other next Wednesday, and we'll continue with the same matter until we cover the whole entire course. So thank you for your attention. If you do not have any burning question, have a nice day and see you next week.
Same.
Same.
Thank you.
Thank you. Cheers.